Hello everyone. Thank you for giving me this opportunity as well. Today I'm going to talk about rare earth elements, distribution in polymetallic nodules or manganese nodules. Firstly, I'm going to just introduce myself and then this project. My name is Wycliff. I'm from the Solomon Islands in the South Pacific. Recently, we have been having this, deep sea minerals. Everyone talking about deep sea minerals, and then we have in the Pacific, our seabeds, and then the seabeds beyond our EEZ. They host many of these valuable marine minerals. So that's how I got myself into this project, and then in this conference as well, which I feel that is important for me to be part of it, so that to get myself involved in the latest developments in marine minerals. This project is funded by, firstly, I would like to acknowledge my other team members, Ian and Colin. Colin is here. This project we are doing in Plymouth is funded by UK Seabed Resources as part of its obligation with its contract signed with ISA, the National Seabed Authority, to provide training to trainees from the developing states. In this talk, I'm basically going to talk about what we are doing in Plymouth, where we are, some of our plans for the future in terms of this project, and then some of the challenges that we face as well. All right, so I'm going to give a brief introduction about manganese nodules or polymetallic nodules, talk about where the samples were collected from, the methods I'm using for this project, and then I'm going to discuss the results and talk about our future work plans for the future, and then I'm going to conclude. So what are polymetallic nodules? Polymetallic nodules, or they are also called manganese nodules or ferromanganese nodules. These are deep sea deposits that are mostly made up of iron and manganese. Apart from that, they also contain some important metals like copper, nickel, cobalt, and critical metals as well, such as the rare earth elements. They normally occur at depths of between 3,000 and 6,000 meters. And they were first discovered in the late 1870s, but then the economic values were actually discovered just lately in 1960s and 1970s. Polymetallic nodules come in different shapes and sizes, from being well-rounded to botryoidal or cauliflower-like, tabular. They mostly range in size from 2 to 12 centimeters. They form by several processes, but the two main processes are the hydrogenetic precipitation and diagenetic precipitation. Hydrogenetic precipitation is when metals precipitate from seawater, which is basically how hydrogenetic crusts form as well, which Sarah has talked about. Diagenetic precipitation is when metals precipitate from the sediment pore waters. So these processes together, they actually contribute to the overall enrichment of different metals in this deposit. Let me just introduce rare earth elements. Rare earth elements, the elements found in the periodic table, they are normally known as the lanthanides. Scandium and yttrium, because of their chemical similarities to the lanthanide series, they are also included. Why are they important? Well, we are all aware of this, that rare earth elements are important in many, used in many of the things that we even use today as well, like mobile phones. wind turbines. And then they are used in high-tech and green tech technology, green tech industries. That's why we are looking for them at the moment. China is producing most of the rare earths, but we are also looking where are the new deposits for these rare earths. Well, the samples for this study were collected back in 2015 and 2013. They were collected from the CCZ, the Clarion-Clipperton Fracture Zone, from the UK claim area, which is this claim area. This is the area of greatest economic potential in terms of nodule mining. At the moment, we have the ISA has granted 16 contractors to do exploration work here, including the UK seabed resources, which is funding this project. So the samples were collected from the UK 1 area, from area 1 and area 2, area A and area B, back in 2013 and 2015, at depths of around 4,200 meters. So 5 box score samples from 5 box scores, where few samples from 5 box scores were given to us in Plymouth, and then those are the ones that we are currently working on. So the methods used in this study are geochemical methods. SEM, we use SEM to look at distribution of the major elements and then the minor elements as well, and then to study the internal structures of these nodules. We use XRF to quantify the major and the minor elements in nodules on glass beads and pressed powder. And then we use ICP-MS for our trace analysis, including the rare earths. So this is the bulk result from, this is average bulk result from the 5 box scores. This is similar to the one which was determined by Lockheed Martin from samples collected back in the 1970s. So Lockheed Martin, UK Seabed Resources is a subsidiary of Lockheed Martin. So this is very much similar. This is similar to the concentration of rare earth, total rare earths, found in nodules collected back in 1970s in this same claim area. These nodules were collected in 2013, 2015, and then the bulk concentration is still the same. If we compare that with other deposits and nodules from other ocean basins, then this is what we get. We see here nodules from Indian Ocean, nodules from the Cook Islands, crusts from the South Pacific, and this is sediment, rare earth-rich sediment muds from the Eastern Pacific. And just for further comparison, the Bayan Obo mine is the main supplier of our rare earths in China. So we can see that rare earths in the CCZ are slightly lower, well lower than the ones in Cook Islands are quite high, lower than these ones, lower than crust and muds as well. But then one of the things that we can we have to keep in mind here is that if these nodules are mined, then this will be mined as byproduct of nickel and copper, which makes them still viable. And all right, so this is one of the things that we do, looking at the distribution of different metals in the nodules. This is a EDS map of this is SEM EDS map of a nodule, which is the backscatter image. This section is mapped for different metals. We can see here the yellow bands are the iron-rich layers, these ones, These are the hydrogenetic layers. These are the layers that are rich in iron compared to manganese. The diagenetic layers are the blue layers here. These are the manganese-rich layer. So we mapped some of the important metals like copper, nickel, and cobalt. Then we found that cobalt is actually distributed in the hydrogenetic layers compared to nickel and copper, which are distributed in the diagenetic layers. This is not new. This is actually well known already. But this is one. I just want to show what we are trying to do with rare earth elements as well. So we tried to study the distribution of rare earth using SEM, but we couldn't get the SEM, the rare earth signals out from our SEM analysis. So instead, we drilled different layers of the nodule. So we get the EDS map, and then from the EDS map we see the different diagenetic. We work out where the diagenetic and the hydrogenetic layers are, and then we drill those layers. And then we get those powders, and then we analyze them by ICP-MS. And then this is what we got for this nodule. So we see here that there are some enrichments. We see that there is some enrichment in this graph here is concentration of rare earths. The lower one is heavy rare earths. This one is light rare earths. And then the total rare earth is a green plot. The x-axis shows the layers, the different layers, 12 different layers, including the bulk nodule as well. So we can see here that nodules, for these nodules, are rare earths actually enriched in these layers, layer number 2, 9, and 11. So if we look here, these layers are this one. This is 2. This is the hydrogenetic layer. This is the yellow band here. The other one is 9, which is this hydrogenetic layer as well. And then the other one is 11, this one. So from this study here, we found that rare earths are actually distributed in the hydrogenetic layers compared to the diagenetic layers. And then we did this one with 2 other nodules, and then the results were same. So we can conclude that they're actually distributed in the hydrogenetic layers. And then we got very few literature on this one. For example, from the first one, this paper here, they studied the distribution of cerium. For these different metals, including cerium as well, using synchrotron XRF. And then they found that cerium is actually distributed in the hydrogenetic layer. This is a more recent paper by Amaya from Southampton. They used laser ablation ICP-MS to study the distribution of rare earths in the nodules. And then they found the same as well. Which shows that our findings are same as some of the previous studies. So now we know that rare earths are distributed in the hydrogenetic layers. Our next plan or work to do now is where are they actually located there? What are the mineral phases that are hosting these rare earths? So this is our next work at the moment. So we've used SEM, but this method doesn't give us, it doesn't give us doesn't show the rare earth signal. So we are going to switch to other methods. We are planning to do diamond synchrotron, diamond light source using synchrotron XRF, using diamond light source, and then we try to study the distribution of rare earths more, and try to see the different mineral phases that are hosting the rare earths. One of the things that we plan to do as well is to date the nodules. and to study their growth rates. At the moment, we are anticipating using osmium isotopic method, isotopic analysis to date the nodules and then study their growth rates. More importantly, to actually look at the different layers and then study what is the actual process, going on in their growth process. So this is one of the papers that was published back in 2005 on osmium isotopic stratigraphy on a crust sample from the Central Pacific. So in this paper, they used the osmium isotopic concentrations at different levels, at different layers. So they sampled a crust sample, and then they took samples from the layers and then studied their osmium isotopic ratios. And then because the osmium ratio for seawater in the Central Pacific is available, you can actually compare with that one and then see what other, try to compare the different layers and then see how they correspond to different environmental conditions or in the past. For example, continental weathering and all that. So this is one of the things that we are planning to do. Thank you. So we found in this project that rhyolithes are concentrated in hydrogenetic layers. What's next? So we are going to look more in detail into these ones and then see what is actually hosting them, and then see how the minerals are distributed, and then try to see how the rhyolithes are actually incorporated in those mineral phases. So this work is still in progress. I've just discussed the osmium dating and growth determination work. We'll see how this will go, and then hopefully in the next meeting or so we'll present some more results on this one, and maybe some exciting results. Yeah. So yeah, I would like to thank some of these people from Plymouth who've been helping in this project. Guys from the Electron Microscopy Center for my SCM work, Alex for my XRF work, Rob for my ICP-MS work, and then all the technical staff in Plymouth Earth Sciences for their support in this project. Thank you.